it a diesel engine or is it a petrol engine? By looking at the compression ratio. As I'm asking a question. This oil engine doesn't really tell us whether it's a diesel or a petrol. It says that an oil engine can be diesel or petrol with a compression ratio of 30. You think it's a petrol or a diesel?
Diesel.
That compression ratio tells me that it's a diesel engine. But you see, 12 and 13 can be the borderline for a petrol engine and a diesel engine. So 13 can be either be diesel or can be 12 and 13 is a borderline. So if somebody say 13 is a petrol, I would say, yeah, but yes, it's petrol, but it's got a very high compression ratio. If it's diesel, yes, I'll agree with it. So 12 and 13 compression ratio is a borderline. So that RC, for now, we assume is diesel. You say that RC is 13. And then we say that uses 10 kg of oil per hour. So the mass fuel rate is equal to 10 kg per hour. And then the heat value or the calorific value, CV, of this fuel is 42 megajoules per kilogram. You must also pay attention to the units. The units are also very, very important. Now we are not dealing with a kilo is megajoules, but when we solve the problem, we convert that megajoules to kilo. And the speed of this engine is 1,800 revolutions per minute. And the question again does not tell us whether this engine is a 2-stroke or a 4-stroke engine, but we will see when we get there. The torque is 250 Newton meters. And then this engine, remember the engine, in order to have combustion, you need air. So the engine that enters, the amount of air that enters the engine uses 3.7 kg per minute. So we say that the mass of air going into the engine is 3.7 kg per minute. Okay, and then remember there's also cooling water. There's cooling water that is used in the engine to cool the engine down. Now, the amount of cooling water in the engine is 12. So MCW stands for cooling water is 12 kg per minute as well. And the temperature rise is 34 degrees Celsius. What is the temperature rise? Cooling water, let's say it enters at 15, leaves at 50, the difference is 34. So delta T is 34 degrees Celsius. That is for cooling water, delta T. Are also used per minute. Okay, that is 12 kg per minute. The temperature of exhaust gases, that is TEX, is 388 very hot gases, degrees Celsius. And the temperature of air, ambient air temperature, TA, is equal to 18 degrees Celsius. That is the amount of air entering the engine. Ambient air temperature is 18. And then CP for exhaust gases. CP, constant specific heat capacity and constant pressure for gases, is 1.26 kilojoules per kilogram Kelvin. Now, the first question says calculate the brake power. The brake power is BP. BP is 2 pi NT divided by 60. I think this one is straightforward, where we say that 2 by pi by N is 1,800. By torque is, where is torque? 250 divided by 60. And the answer is 47.12 kilowatts. This one is very straightforward. Now the second one said calculate fuel consumption per kilowatt hour. Again, the problem here that they did not mention. Okay, the reason why they didn't say specific, so they didn't say brake specific fuel consumption is because we only have brake power. There's no indicated power. So they decided not to use the word brake. But the actual question should be determine the brake specific fuel consumption. B, brake specific fuel consumption, which is given by what? It's given by the mass of fuel divided by BP, which is 10 divided by 47.12, and the answer is 0.2122 kilojoules per kilowatt hour. So this engine, it needs 0.2122 kg of petrol or diesel to produce 1 kilowatt in 1 hour. Number 3, the brake thermal efficiency. C, the brake thermal efficiency, BTE, is equal to brake power divided by fuel power multiplied by 100, which is 47.12 multiplied by 3600. 3600, remember we are converting what? Seconds to hours, because 47.2 is in seconds. Or we are converting 10 kg per hour to per second, so that the units are homogeneous. 4200. And the answer is by 100 is 40.4%. Okay, so the relative the relative efficiency on a brake power basis, assuming the engine to work on a constant volume. Okay, you see now the question said that we assume that it's an Otto cycle. In other words, a petrol engine, but that compression ratio shows that it's a diesel. But now we are assuming that it's Otto cycle. That's what the question is saying. So what we need to, okay, so the formula for question D, the relative efficiency is going to be brake thermal efficiency divided by Otto cycle efficiency. Otto cycle. So Otto cycle efficiency, we know that which is 0.404 divided by the formula for efficiency for Otto cycle is 1 minus 1 divided by compression ratio, which is 13, 1.4 minus 1, and the answer is multiplied by 100. And the answer is 63%. In other words, we want to know the ratio of brake thermal efficiency and the Otto cycle. Otto cycle, we discussed that last week, so we know what Otto cycle is. Relative efficiency is 63. Now comes the most important part of this question, the last one. Last one. The last question says, draw up a heat balance in kilojoules per minute as well as in percentages. Now, what is it that we are looking for here? So according to this question here, the heat that has been liberated by fuel in the engine, some of that heat came here, was converted into power. Some of that heat was stolen or was absorbed by the cooling water. And some of that heat was stolen or taken by exhaust gases. So the question says, draw heat balance and then show us how much the percentage of heat that was converted into work, the percentage of heat that was taken by the cooling water, and the percentage of heat that was taken or stolen by the exhaust gases when they leave the engine. That's what we have to do. So we are now going to draw a heat balance, and it must be in kilojoules per minute. At the end, we sit down and then we assess whether this engine is efficient or not based on the answers that we have got. So heat engine, we are going to have two columns. So heat in kilojoules per minute. The second column, we draw a line and then we say heat in, heat out. Heat out in kilojoules per minute. And then here we're going to have a percentage, the percentage. So on the left-hand side, heat in. Now heat is coming from only one source, which is fuel. So we can say that fuel, heat coming from fuel is given by the mass flow rate of fuel multiplied by energy value of fuel, which is CV, which is equal to mass flow rate is 10 multiplied by 4,200. Right? Now, it's because it's per minute, we have to divide by 60. This 10 is per hour, so we divide by 60 to make it per minute. Now, 7,000 is the source of heat or source of energy for this particular engine. 700 kilojoules per minute, that is the amount of heat coming from fuel. Now we want to see from this 7,000, how much was converted into work, how much was taken by exhaust gases, and how much was taken by cooling water. So we start with the first one, where we say A is BP. BP is given by, we already have the BP, which is 40 watt. BP, we said, is 47.12. 47.12 kilojoules per second. Now we multiply by 60 to make it kilojoules per minute. Multiply by 60. And the answer is 27, 28, 27. 28, 27.2. This is the amount of heat that was converted into work. The second one, we have to calculate the amount of heat that was absorbed by cooling water. And then we say Q, W is going to be the mass of cooling water multiplied by Cp for cooling water multiplied by delta T for cooling water. Right? Now cooling water, the mass of cooling water is 12, is given 12 kg per minute, 12. Multiplied by Cp for water is always 4.187, always. So please pay attention to this as well. It's always 4.187. This is Cp for water. If it is not given, always 4.87. Okay. So multiply by 4.187. I'm sure you know this from fluids. Multiply by delta T. Delta T was given as 34 degrees Celsius. 34 degrees Celsius. And the answer here is 1705, 44. And then the last one, some of the heat was taken by exhaust gases, because when the exhaust gases leave the engine, they are very hot. So it means that they have taken some of the heat. So we say that Q, exhaust gases heat, is going to be the mass of exhaust gases, EX, multiplied by Cp of exhaust gases, multiplied by delta T for exhaust gases. Right? The mass of exhaust gases, what? Is going to be the mass of air coming into the engine plus the mass of fuel. They give you the mass of exhaust gases. So in this case, we will say that 3.7, which is the mass of air, plus 3.7 is in kg per minute. So we convert fuel to kg per minute by dividing by 60 because it's already per hour. Bracket multiplied by Cp is already given, it's 1.26. 1.26, and the temperature difference is given. Outlet temperature is 388, and inlet is 18. And then we get 1802.64. So 1,800 has been taken by exhaust gases. The last one, now we conclude. We want to know some of the gases that is, some of the heat that is unaccounted for. We don't know what happened to that heat. Some of the heat maybe is due to radiation. Remember, when you open your engine or your bonnet, there's a lot of heat coming from the engine. That is heat due to radiation. So in this case, you can see that unaccounted for heat, Q unaccounted for. Unaccounted for. So the heat that is unaccounted for, it is going to be total heat supplied, 7,000, this 7,000 here, minus the sum of all, which is 27.2 plus 1705.44 plus 1802.64. And the answer is 664. Okay, let me put it here. 664.72. So 664.72 of heat, we don't know what happened to it. We don't know. That's why you see it's unaccounted for. Some of this is due to radiation, of course. But now this information, as it is, does not make sense to us. So we have to make it. You have to make it to make sense by converting it to percentages. So we want to know the percentage of the heat that is available at the wheels. In other words, we say 27.2 divided by 7,000. Now we know that 40.34 of the heat in the engine has been converted into work. Similarly, we say 1705.44 divided by 7,000, 24.4% of the heat generated has been absorbed by cooling water. And then thirdly, we say that 1,802 divided by 7,000, 25.75% of that heat has been absorbed by exhaust gases. And lastly, 9.45%, we don't know what happened to that heat, which is too much. You can't say that it's almost 10% of the heat. You don't know what happened to it. So when you add all of this, they must give you 100%. When you add all of this, they must give you 7,000. So this is the heat energy balance. At the end of the day, now you have to analyze this engine and check, are you happy with the performance of this or the heat distribution in this engine? I wouldn't be happy because of that unaccounted for heat. That heat is actually is very high, 10%. I think the acceptable one is only 5%. Now, when you're talking about the engine, I mean the ideal engine, this is how it's supposed to look. Ideal engine, we will say that A is going to be VP. The percentage of VP is supposed to be 30%. That is the amount of heat converted into VP. The second one is going to be friction power. Friction power is supposed to be 5%. C is supposed to be heat absorbed by exhaust gases, supposed to be 30%. D is supposed to be heat absorbed by cooling water, supposed to be 30%. And then the last one is going to be unaccounted heat, Q unaccounted for, or we can say due to radiation. Radiation is 5%. This is an ideal engine. You add all of them, they give you 100%. In our case, we do not have friction power. Why? Because we do not have indicated power. If we had indicated power, we already have BP, then we would have calculated FP. So you will make use of the information that you have. The one that you don't have, don't worry about it. Even in the lab next week, you won't get, I'm not sure if you'll be able to get indicated power. If you don't get indicated power, it means that this FP is going to fall away. But ideally, if your engine is giving the following information, then we say that your engine is perfect. So 30% must go to BP, 30% must go to exhaust, 30% must go to cooling water, 5% must go to friction power and be unaccounted for. This is what we call a heat energy balance sheet, where you balance the left-hand side with the right-hand side. This is not difficult, people. So please go and redo this question. And then if you have questions, I know that there will be questions here as to what happened here. What happened here? I know. What happened here is simple. For you to get exhaust gas is actually what? The sum of air into the engine plus fuel. So this is air and this is fuel. So we add the two, they give you a total of exhaust gases. That is a simple explanation of